logged on. Okay, so everybody should have a big orange slide on your screen. I assume that's the case. Are we ready to go, Paul? Okay, you're muted, but that's okay. All right. So the title of the talk is Grounding and Bonding for Home Stations. There's an extended version of this talk in 4 parts on the ARRL website, and it also includes a section on mobile stations and stuff like that. So there's an expanded version, but this is the fire hose version of the talk. And I like to thank Contest University and ICOM America for originally promoting this talk and sponsoring Contest University, where it originally came out. Okay, so the goals of this, first thing we're going to do is talk about the difference between ground and bond. We throw a lot of words around. We don't use words as precisely as we should, and there's a lot of confusion between the different types of ground and the different types of bond, and not really sure what the difference is, but they are different and they're related and they're both important. Then we'll be able to appreciate these different requirement sets, and I'm an engineer, so I use the requirement word a lot. You've got AC safety to worry about, you've got lightning protection to worry about, and RF, managing the RF that's in our station. And previously, most of the information about this was spread out over different sources of information, so it's very confusing to people. Sometimes they use the same word to mean wildly different things. And after a series of 3 columns in QST about 10 years ago on RF grounding and bonding and all that kind of stuff, we got a lot of correspondence about it, and I talked to Steve Ford and I said, we need to collect this information and put it in a book. And so that's where the book came from. And that helps people deal with this completely different sets of requirements. Hams have to deal with a very wide range of frequencies, more than almost any other service. So this is important to us. And so we'll discuss some of the issues that are involved there. And this is not a cookbook talk, as in first you do this and then you do that and then you do this, because there's too many different circumstances. It's more of a toolbox talk where I talk about the issues and some techniques for you to apply, and then you go home and you look at what your circumstances and budget are and decide what to do. You'll find out that I keep stressing this: one common system satisfies all these requirements. You don't have to build an AC safety system and a lightning protection system and an RF management system. Build one solid system and it will satisfy all of these requirements. And then at the end, I'll list some comprehensive resources. And Paul, I will send you a PDF of the slides so that you can post those and feel free to be sharing these with the group. There's no copyright issues here, and that way you don't have to worry about what was that URL that he said and all this kind of stuff. So it'll be in the slides.
We'll just buy your book.
Yeah, exactly. Okay, so your ham radio references. If you've got a recent copy of the ARRL handbook, my last issue as editor was the 100th edition in 2023. Greg Lappin, N9GL, is the new editor, and he's maintaining 99.9% of the information. A lot of this information is in the handbook, in the station construction chapter, and then the ARRL antenna book under electrical safety has much of the same information as well. So those are, if you've got the last couple of editions of those, you've got a lot of information there. Ron Block, NR2B, was one of the original Polyphaser employees, and he wrote a series of 3 articles that are free in QST, lightning protection for the amateur station in June, July, and August of 2002, and they're still quite good. Now, those are available in the technology section of the ARL website. And I forgot to grab this one book. Here we go, it's right here. And this is Ron's new book. He got a cover plaque for an article about 1.5 years ago. It's called Lightning Protection, a Comprehensive Guide for Amateur Radio. And he really does a deep dive on lightning protection. So if you're really interested in that, get Paul's book. It's not expensive, and you can order it online. And that will be in the PDF slides, or I'll send a link to Paul. Power grounding, bonding, and audio for amateur radio. That sounds pretty comprehensive. That's a great tutorial by Jim Brown, K9YC, and he also wrote RFI ferrites and common mode chokes for hams. Both of those are excellent tutorials. If you go to his website, you will find many such presentations and papers and all this stuff, and it's worth having him on your bookmarks. Those are 2 comprehensive resources for you. And then the WHAI website has some more information. Tom lives on a mountaintop in Georgia with a 300-foot tower on it, and he knows a lot about lightning and surviving lightning. And then for mobile stations, the K0BG website is your go-to. And then this is my favorite, of course. You know, I've got the grounding and bonding book here. This is the 2nd edition, which was expanded somewhat from the first to talk more about special topics. We have some more drawings, and there's more about, for example, 2nd floor or upper floor stations. I'm in a 2nd floor station myself, so I have to apply different techniques than somebody who's in the basement or right at ground level. So anyway, we have more information there. The book covers all these different sets of requirements. The reviewers were excellent, along with Ron Block and Jim Brown. Also had the ARRL lab review it, and Dale Svetnov, WA9ENA, just recently became a silent key. He's a was a well-known lightning consultant in the upper Midwest. So those guys really kept me out of the weeds. Everybody thinks I'm a tremendous expert on this stuff, and really it's the experts that came along and helped make the book true and factual and useful. All those guys get full credit. Okay, so let's talk about these terms. With ground, when we talk about ground, everybody seems to know what ground is, but it can be 3 different things. It can be a noun, which refers to an actual connection to the earth, and that's typically used in AC and lightning protection. It can be just a local reference potential, like in a circuit. Talk about circuit ground, analog ground, digital ground, that kind of thing. Airframe electronics, avionics guys talk about ground, but I haven't seen an airplane dragging a chain yet. So what they're talking about is the local reference potential in the plane. So that's how you talk about this local reference potential at RF and for circuits. You talk about ground. It can also be a verb, which is an action, which means connected something to the reference potential. I'm going to ground this input. I'm going to short this capacitor to ground, that kind of thing. That's actually an action. It's not describing a thing. And then finally, it can be an adjective. So it's a type of connection, such as ground conductor or a ground system. And you hear people using the word ground, talking back and forth to each other. And they are both nodding up and down in the right direction. But if you listen carefully, you can find out that they're really talking about all 3 different things. So we have to be careful in the way we use the term. The British use the term earthing, which means the earth connection. If you're going to earth something, that means you're going to connect it to the earth. And so that's a lot clearer, but our term is older, so that's what we get. And you can hear sentences like, I'm grounding the chassis to ground with a ground wire, and those three uses of the word all mean different things. So we have to be careful about that. And there are some myths about ground. We tend to think of the earth as this big magic 0-volt thing. And if we connect anything to it, it's going to be 0 volts, right? Well, it's not a magic sink, and you pour RF or lightning and so it just magically disappears. It's gone. And we have the same notion about a vehicle body. It doesn't work that way. The earth is a very complex volume of material. It has resistance, it has impedance, it has permittivity, it has permeability, all these different things. It's not a magic 0-volt reference. So we have to remember that when we start talking about lightning protection systems and high currents and how do we connect to it. There are also some fuzzy definitions. RF ground is a term that I try not to use because it gives the impression that you can create some kind of 0-volt reference, either a surface or a connector or something like that, that's going to be at 0 volts at all frequencies, and it just doesn't work that way. You can have 0 volts over a range of frequencies, and that's 0 volts with respect to something else. But we have such a wide range of frequencies to worry about that creating a quote RF ground is really not something that's possible. And what it really means is something that's electrically very small, so you can maintain the same potential, whatever it is. It might not be 0. You want the same potential across whatever structure you have there, whether it's a wire or a circuit board or an enclosure or whatever. So be very careful when you use the term. Then there's these ground loops. Everybody knows that ground loops are bad, right? Well, if you look behind your equipment, even for a modest station with just a few devices, any closed connection between enclosures that comes back around, that's continuous, that's electrically continuous, is a ground loop. And anytime you have, say, a couple of coaxial cables with PL259 on one end and a PL259 on the other end, and over here you have a PL259 and a PL259, you've got a ground loop there, and you're never going to get rid of them. There are literally dozens, if not hundreds, of ground loops in a typical ham station. So what we do is we manage them. The main concern of ground loops is for AC power wiring. You don't want a loop that can carry large neutral currents or something like that, or audio people who don't want ground loops because they pick up magnetic fields and you get hum. But at RF and up, typical ham frequencies, there's nothing you can do about it. We just deal with ground loops by bonding. Essentially, we short them out. We'll talk more about that later. And then this term single point ground, this also comes out of the power field, where you want everything connected to one single reference point so that large error currents and neutral currents and these rectifier currents and all these other things that happen in the AC world, AC power world, you want them to not have a path through all of your conductors. So you connect everything together to one single point. Well, if you try to do that in a ham station, what you create is a whole bunch of large loops, and each loop, each path through the conductors picks up RF, and the amount of field that it encompasses determines how much electromotive force or voltage causes a current to flow in that loop. So you want to minimize the area of your loops, and you don't do that with a single point ground. What we're going to talk about instead is bonding. We have an electrically small, meaning in terms of a wavelength, electrically small structure such as a pipe or a sheet of metal or a wire that is so small that everything connected to it pretty much is at the same voltage. Not zero, but it's about the same voltage. And the idea is everything goes up and down together, and that's really important, particularly with lightning. So each one of these sets of requirements, AC safety, lightning protection, and RF, managing the RF that's flowing around your station, they use the term ground differently. You just have to be very careful about what you're referring to, what you're trying to accomplish when you use the word ground in a ham environment. All right, let's jump over to bonding. And if you go and look in the dictionary for electrical engineers, all that bonding means, it's a connection intended to keep 2 points at the same voltage. That's it. There's no complicated explanation or circumstances or equations or all that kind of stuff. It's just a connection between these 2 points that you want to have bonded together. And the important thing in a ham station is for these points to go up and down together. You're going to see me talk about that a lot. If you have the same voltage at these 2 points, you won't have any current flowing between them. Current flows because of a potential difference. If you've got a voltage over here and a voltage over here, and there's a connection, then current will flow from the high voltage to low voltage. And so what we want to do is minimize this current flow, because that's what causes interference. You also prevent shock hazard from voltage differences. If you bond everything together and that's connected to your AC safety ground, then if there's a fault in insulation, if something is a short circuit, who knows, then by bonding everything together and then connecting it to your AC reference point, you prevent shock hazards. And if there's leakage current, for example, maybe there's insulation that's starting to go bad or something like that, leakage current will also flow back to the AC safety point. But you have to have everything bonded together so that this piece of equipment isn't at a different voltage than the other piece of equipment. That's when you have a shock hazard. So bonding is important there. Lightning surges can cause enormous destructive voltage differences just because of the amount of current involved and the strong magnetic fields. You can really generate some incredible voltages in conductors, surprisingly high. So by bonding all your equipment together, even if there's a lightning surge through the station, you keep everything together. So it goes up and down. If you've ever had a boat out on a lake or something like that, and you see a floating dock, for example, that's exactly what they're trying to do there. They want that dock and the boats and everything to go up and down together so that one boat isn't trying to do one thing while the dock is trying to do another. And you wind up with things tearing themselves apart because of a big wave from a boat or something like that. Everything goes up and down together. So you're creating a floating dock electrically. And to reiterate, when you bond everything together, you limit current that flows between the devices caused by picking up RF. You're very close to your antennas typically at a ham station, so you're going to have very strong RF fields in your station, and that means you're going to have RF current flowing on the various pieces of equipment. If you bond them together, then that helps limit the amount of RF current that's going to be flowing between them. And the RF current getting to where it should not be is what causes the RFI. It's not the voltage, it's the current. And if you can minimize voltage, then you minimize current. For bonding to work, meaning to satisfy that need that you're trying to keep everything at the same voltage, it has to be low impedance and it has to be electrically short so it doesn't start acting like an antenna. 6 meters and VHF 2 meters, that's where ham stations encounter conductors that are starting to look like transmission lines because the wavelength is starting to get pretty small. And so to make it electrically short, meaning say less than a 20th of a wavelength, then you've got a limit on how long these things can be. If you're talking about 60 hertz, the wavelength is 50 million meters, and so electrically short, it can be as big as a football field and still be electrically short. But at ham radio, starting up around 40 meters, 20 meters, that kind of thing, you start to see transmission line effects in conductors. And so you want to keep everything electrically short. Low impedance means low inductance and low resistance. So there's low resistance counts at AC and low inductance counts as you start going up in frequency. We'll talk about that in a minute. The bonding also has to be heavy enough to carry the expected current. If you're talking about bonding something together, say a tower and a ground rod or something like that, and you think it might get hit by lightning, we're talking about kiloamps. And that is a little scary to circuits guys like me. The conductor itself has to be heavy enough to carry that current and survive, and not just vanish as an arc where everything gets blown up. So that's why you see this reliance on number 6, number 4, number 2, double knot. These big wires, they have to be heavy enough to carry the expected current. And they also have to be sturdy, especially if they're outside. So if you've got wires that are buried into your yard as part of the lightning protection system, maybe you've got a bonding wire going from your house over to a tower nearby or something. It has to be heavy enough to stand frost heaves and being dug up. And what if you hit it with the rototiller? It's got to be heavy enough to jam the rototiller. Don't ask me how I know this, okay? If you don't have a heavy enough conductor and you damage it, you can cut it. Suddenly you haven't got a ground connection. And so if that conductor doesn't resist damage or mechanical insult, whatever, when you drive over it or whatever, then you'll never know that you don't have a ground connection. So these bonding connections have to be heavy enough mechanically to survive whatever the environment is. Inside your ham station, what do you use for bonding? The commercial standard is strap, solid strap, 20 gauge, about 1.5 inches, 2 inches wide, or heavy wire. Number 14 works really well. For example, all that N0AX that you refuse to throw away, all those little short pieces of, they're in a box in your garage. I know this, I've got a box. Okay, that's perfect for bonding conductors. So you just strip off the sheath and you've got 3 nice pieces of solid copper wire to use, and it works really fine. Even though it's round and it looks small, it still has a fair amount of surface area. Even really wide strap stops being all that effective because the current tends to concentrate at the edges. And so a heavy wire, heavy round wire will work as well as a 1 inch or 1.5 inch strap. You can use that flat weave tin braid, the silver stuff, if your equipment moves around or you have to continually move the ground connection around. Whatever you use for braid, you've got to protect it from moisture and chemicals. As soon as it gets wet or dirty, what happens is all those little wires that are braided together, the water and the chemicals get in there, and instead of making a good connection, they start getting corroded. And so what happens is it looks fine, but the problem is at RF, it's going to cause noise. It's going to create noise for you. We don't like noise. Maybe the AC guys and the automotive guys, they don't care so much about noise, but we care about noise. So protect your braid from moisture and chemicals. Never use braid outside, for example. And if you want to use the braid from old coax, do not take it off the center the center dielectric. The minute you take that jacket off and you expose the braid, what happens? Oxygen gets to it, water gets to it, and you loosen it up to get it off that center thing. You're kind of sliding it back and forth. And all those little connections, the jacket was there to hold them tight against each other and protect them from oxygen and water. The minute you take it out of the jacket, all that protection is gone. And so it immediately begins to degrade. If you want to use old coax braid as a ground conductor, leave it in the jacket, waterproof it at each end, put a terminal on it, and just use it as a, quote, big ass wire, okay? It will work fine. Don't take it out of the jacket. So if you follow these simple rules on bonding, and none of this has to be expensive or ridiculously hard to do, it works in your favor for AC safety, for lightning protection, and RF management. So just get used to bonding with the right stuff and materials and techniques, and it will pay benefits all through your station. Okay, let's jump over to AC safety grounding. AC safety grounding has several names depending on where you live in the country and how old your electrician is. The current preferred term that you'll see in building codes and reference manuals and things like that is equipment ground, and that's a connection back to the reference point in your AC power service. It can also be called third wire ground because you've got your two hot and neutral, and then you've got the safety ground over here. So that's the third wire. It can also be called the green wire ground because it's usually insulated with green insulation to indicate that it's a ground wire. So the whole purpose is to connect whatever it is all the way back to your AC service panel reference point. Ground connections in AC, to be effective at AC, need to be low resistance. Their function is to carry all of the possible fault current in a branch circuit until the protective devices remove power from a circuit, whether that's a fuse or a circuit breaker. You want the ground wire to carry all of the fault current, if you've got a short circuit or whatever, until the circuit breaker pops. The whole point is to remove power from the circuit and not have a fire start. So what's important there is not necessarily the inductance, because we're talking about 60 hertz. So the important thing is resistance. You want the ground wire to be as big or bigger than the conductors that supply power to your station. There are two purposes to this ground wire, and only two. One is it provides a path, a safe and controlled path back to your AC common point for fault current, shorts, leakage current, as we just discussed. And all these earth connections, because your AC service, if you look at the box, there will be one big wire that goes to a ground electrode, whether that's a rod or an UFR ground or whatever. That earth connection, there's thousands and thousands and thousands of these in a utility power supply system. Every house has one. Sometimes every pole has one. All of the substations have one. The whole point is to stabilize the power system during faults or transients, such as lightning, or maybe there's an accident on the road, maybe a tree falls into the line, whatever. The whole idea is to stabilize the power system so voltages just don't start going wildly in all directions when there's a problem. So two reasons: a path back to the AC common point for fault currents that protects you and it protects your house and it helps it keep from burning down. And the other thing is to stabilize the power system. Okay, and if you're not real sure about what you're doing with AC wiring, and I know we're all licensed radio amateurs, so we automatically have been given all electrical knowledge. But I know most of us, we can install a branch circuit, we can install switches. Some of us, the advanced students, can even install a three-way switch. Okay, there are so many different options now. I don't know when the last time you went to the electrical section at the hardware store was, but there are so many different devices out there. We can easily get out of our comfort zone real quick. So get a how-to reference. This one's my favorite. I've got a copy of the previous edition here. It's a decently sized book. It's got lots of pictures and everything. It shows you how to do it right the first time. Dimmers, four-way switches, all these different things, hooking up appliances, all those different weird dryer plugs and stuff. And it also tells you what not to do, like do not connect grounds to your gas pipes and stuff like that. So that's really important to have a guide to show you exactly what to do so that it's safe. Another good option, if you really want to get into it, this is a rather large book. Okay, this is the NEC handbook, the National Electrical Code handbook. The actual code is a little book. It's not very big. It's like this. It's about that thick. But it's just full of rules. It doesn't explain the rule or anything else. It's like a legal document. It's just the code, National Electrical Code. It doesn't tell you why or how. Well, that's what this book does. And it's available at your library. And it goes through each one of the code requirements. And it tells you why the code requirement is what it is. Also has drawings and pictures of how to satisfy the code, typical installation issues. You don't have to know all this stuff. Hams are basically interested in Article 250, which is about grounding. Articles are chapters in this book, and the Article 800, which is about antennas and feed line. You can go down to the library, you can get this book, and you can make a copy of those sections if you want. These are available online. When I bought this, it was $35. It was an edition that's been superseded. It wasn't the latest edition. It was a couple of editions old, but the requirements in the grounding and the antenna sections rarely change. So you don't have to have the latest thing. Anyway, it's a pretty impressive book to have on your shelf. There's particularly some special rules for subpanels and outbuildings. A lot of us have a station in the house somewhere, and we want to run a subpanel so we can have a master disconnect. Maybe we got amplifiers, what have you, and so we run a 220 out to the garage or whatever, and we have a subpanel, or in the basement, or maybe there's an actual shack in the backyard. Look into the rules for subpanels and outbuildings and make sure you follow them. It's really easy to create significant shock hazards by improper grounding of subpanels, and people are electrocuted every year. Don't be one of those people. They also talk about how conductive concrete is. You would think concrete would be an insulator. Nope, it's actually pretty conductive. And so people are walking around in their bare feet, particularly in the summer, in the basement, whatever, and they touch something live and it goes right through them into the concrete. They're electrocuted. So it's very important to follow the special rules for subpanels and outbuildings. I also recommend that if you do anything significant beyond installing a branch circuit or lighting or something like that, hire a pro electrician or an electrical inspector to come out and just look over your shoulder. Yeah, hey, looks like pretty good job there. Or what's really valuable is they come and they look at your work and they go, you really don't want to do that because it's going to cause a problem. So the time to figure that out is before you start applying power to it and all that kind of stuff. So hire somebody that knows what they're doing. No big deal. And then remember, local code is the law. It's called the authority having jurisdiction. It can be your town, it can be your county, whatever. And they'll have building codes. And yeah, the building codes are a pain in the neck to comply with, but the idea is to prevent shock hazards and prevent fires and that kind of thing. The original National Electrical Code was created by the National Fire Protection Agency, and that tells you a lot about what the danger was. When electricians started wiring things up, electricity became a thing, stuff was getting burned down, people were getting electrocuted, and so the fire department is the one that came up with the idea of an electrical code. And if you want to get insurance coverage, you might get, and you didn't follow the code and your house burns down, you might get a payment from your insurance company. You might not, but you'll probably have trouble getting insurance from them a second time. So local code is important. It's not there to make your life miserable. It's there to make your life longer, etc. All right, let's jump over to lightning protection. Lightning comes from way up there, or at least it goes way up there, 50,000 feet, 30,000 feet. You can't steer it, all right? It's already made its decision by the time anything starts happening at our level, okay? So you're not gonna put up anything that's gonna force lightning to suddenly go over here and go into the ground. You can't do it, but you can help lightning make the decisions, okay? What does lightning want? Lightning wants a heavy, direct path to the earth so that it can dissipate charge into the ground. Lightning is just a regular rebalancing of some kind of charge imbalance between down here and up here. Whether it's negative, positive, or negative, positive, doesn't matter. There's just enough charge imbalance so that the air breaks down and creates this arc between A and B so that the excess charge, whichever direction it is, can flow and reduce that voltage imbalance to a small value. So basically it wants a heavy direct path to the earth. Now we talked about resistance for AC safety, and lightning is sort of an AC event. It's not strictly a DC event. It's a big pulse, and it might have AC components in it. It might go positive, negative, you know, that kind of thing. It takes a lot of AC components to create a big pulse. And so it's an AC event. It's not just a DC event. And it has components from down close to DC all the way up through VHF and UHF. That's why we can hear it in our receivers, even at 2 meters, even higher. When there's a thunderstorm, we hear like that. That's the AC components of lightning that are radiating because there's current flow. And if there's current flow that's at that frequency, it's going to radiate a signal just as if you had an amplifier making it. So the important thing here is if you want to have a strong bonding connection, then you want the minimum amount of inductance, because the voltage across any conductor is the amount of inductance times the rate of change of current. And the higher the frequency, the higher the rate of change of current. You might think of it as L, the inductance, times delta I, the change in current, divided by delta T, which is the change in time. So a sharp, short pulse has a very high delta I over delta T. And it doesn't take very much inductance to cause a significant voltage. Here's an example. You have a number 12 piece of wire, 1 foot long. Number 12, it's straight, it's not coiled up or anything. It has about 300 something nanohenries. If I hit that number 12 wire with a typical lightning pulse, which is 1 kiloamp changing at the rate of 1 kiloamp per microsecond, and that's by no means unusual. That wire carrying that current pulse will have 761 volts across it, just from the fact that we have a rapidly changing current flowing through a wire that has some inductance. So you want to minimize inductance so that whatever fast changing current flows through it creates the smallest amount of voltage across it possible. Okay, all of these paths for getting the charge back to the earth, they need to be a low inductance and they need to be outside. Okay, don't run grounding and bonding conductors that are part of your lightning system inside the house. Don't run them through the crawl space. Don't run them through the garage. Don't run them through the attic, because they're carrying significant amounts of current and will have significant amounts of voltage across them. So all that stuff, your perimeter ground system with the ground rods and the radials and all that kind of stuff, outside, run it along the foundation, that kind of thing, but don't bring them in the house. Don't give Mr. Lightning an invitation to come in and flow through your house. And don't make it easy for lightning to flow through your station on the way to the earth. There's a lot of people, and for a while it was me until I got wise and read my own book. They have an entry panel. Oh, it's a very nice entry panel, and we'll show an example of this. But then all of the cables were in the house, and then they connected to the station, and then they connected to a power supply, and then they connected to the AC service entrance, and there was a ground rod over there. So Mr. Lightning will come and flow through your station, and when Mr. Lightning flows through your station, stuff gets damaged. Let's talk about this single point ground panel. The whole point of a single point ground panel is to bond all of the grounds of all of your entry paths. And that's all your feed lines, all your rotator control lines, all your power stuff. And if you can also include your data service, your telephone service, your cable TV, whatever, on this panel, that's so much better, because all the grounds are bonded together in one electrically small volume, and then you can connect them to whatever ground system you have. That's usually called a perimeter ground because it's a conductor that flows all the way around your house. It doesn't have to go all the way around. We often can't make it a complete loop because of driveways or patios or whatever, but you want this big system of grounding electrodes outside your house. That's called your perimeter ground. And you mount all of your protectors on this panel right together, all the lightning protectors, all the little multi-line protectors for rotator control lines, whatever your telephone and data and TV services have. You want all of them in as close together as possible, so that when there is a surge from lightning, what happens is the protectors all fire at the same time. If they don't all fire at the same time, you will have this point at a really high voltage while this arrestor has fired, and then a little later this one will fire, so it's down here, but this one is already done. And so you have really high voltages between different ground points in your system, just because they're located at different points and the current doesn't flow at an infinite amount of speed. It flows at the speed of light, and so you can have transient voltages that are quite significant between different ground terminals in your system. Minimize the voltage differences due to the timing and keep everything going up and down together. Your single point panel should also include an AC power protector. If you can run your branch circuit over to this panel, mount a big surge protector on the panel, and then run a protected circuit over to your station. Typically, most stations can run on one 20 amp circuit from an AC system. Now, if you've got amplifiers or something like that, those will require an extra circuit, of course, but most modest stations can run off a single branch circuit. And you want to keep your protected and unprotected cables separated. What does that look like? Okay, here's kind of a sketch of a panel, and I'll use my cursor here. Here's the panel. It's just a big piece of metal. It can be aluminum, it can be steel, it can be copper if you really want to pay a lot of money, but just an aluminum panel is great. And then you mount all of your protectors on the panel. Here's the feed line arresters that we're familiar with. Here's a multi-line rotator protector. Here's the protector for data or phone. And here's the surge protector mounted on the panel. Okay, these are the unprotected lines. All this stuff down here it comes in from your AC service. It comes in from your antennas, your rotators, all this kind of stuff. And when any technician shows up with one of these service boxes for phone, for data, for TV, whatever, they are required to connect a ground point in that box to either a dedicated ground rod of its own or to connect it to your AC service ground rod, or if you tell them, hey, I've got this perimeter ground system out here around my house, they can connect to that too. But they're required to connect these service boxes to some kind of ground electrode. This is all unprotected. This is all exposed to lightning transients. So what you want to do is keep those cables around. Excuse me, I have a friendly cat here. Her name is Electra. Anyway, you want to keep those cables away from the cables that then go into your station. It looks a lot nicer if you bundle everything together and lace them up or use tie wraps or whatever. The problem is if you do that, lightning will jump from an unprotected cable to a protected cable, and it will defeat the arresters and your grounding scheme. So have two bundles. One is your protected stuff and one is your unprotected stuff. Here's a typical example of a single point ground panel. This is K4RO's panel. Kirk lives on a high ridge west of Nashville, Tennessee. That's why his signal's so loud. But the problem is he was getting hammered by thunderstorms, and every time a big thunderstorm would come through, something would get blown up. Some switch, a filter, a box, a power meter, something. And he got fed up with that. And his station is on the main floor of the house. It's just above a drive-in garage. So he drives into the garage, his station's up here. Okay, so what he did was mount a big sheet of aluminum on the side of the garage. You can see the cinder blocks there. Here is his big ass wire. It connects from the sheet. It goes outside through the cinder blocks to his external ground system. And he mounted everything having to do with the antenna system on this panel. You can see filters, you can see switches, you can see selectors. There's a stack match here, all this kind of stuff. It's all mounted on that panel. And that panel bonds it all together. And then this wire bonds it to the lightning protection system outside. Since he did this, he's lost exactly 0 pieces of equipment. And it's been several years since he's done this. So this really worked for him, this bonding together and making sure that everything goes all up and down together. So there's no big opportunity for current flow between, say, this filter and this switch, or this stack match and this rotator controller, whatever. They're all at the same voltage. It's not 0, but they're all going up and down together. Here's an example. My station, I'm also on a ridge. I'm not as good a location as Kirk is, but it's pretty good. And so it's exposed. And when I bought the property, I walked around the property and there were a lot of burned trees. And I said, well, that's the large print giveth and the small print taketh away. If I'm going to have a good station, I'm going to have to deal with lightning. So at the bottom of each one of my three 60-foot towers, I have this single point ground panel at the tower base. And all this is a surplus fiberglass electrical box with a piece of plywood inside. Here's the piece of plywood and some aluminum flashing. It's just the basic aluminum flashing. You go down and you get it at the store, get it in a roll, 10 feet, 15 feet, whatever. And I just use sheet metal screws to tie it to the plywood. And then I mounted my antenna switch. This is an RCS4L, and that was a 4-position remote current, coax switch. Here's the input to it. It's a hard line that runs back to the station. And then here are the antennas that are connected to the switch. You can see my big ass grounding wire here. It's number 6 AWG. I just bought a spool of it off of eBay, and I just have a big spool of number 6 in the garage so that I have the right stuff whenever I need to do grounding. And that goes to a ground electrode. And then these, now I'm going to save you some serious money. Okay, we've all looked at rotator control cable, which has the 2 number 16s and a bunch of number 18s, and they're all in one jacket. It's all very convenient, and it's all very expensive. I think it's over $1 a foot now. So if you have a long run of this stuff, you can spend a lot of money just on the wire. So what I did instead was, if you look at this, what it is 10 conductor irrigation or sprinkler system control wiring. And it's sold by the 1,000-foot spool. It's just sold at really high volume. This is a direct bury jacket right here, and each one of these wires is a number 18. So for the solenoid circuit, that is the heavy one on most rotators, you double up these number 18s and they make a dandy number 16. So I've got 10 conductors, and with 2 pairs made out of some of the wires, that leaves me with a total of 8, and that's perfect for running a rotator, your typical ham-in or tail twister or what have you. And then each one of these wires has a gas discharge tube, cost about $1. You buy them in a box of 100 from Mauser Electronics. You get the 75-volt ones, which are the small ones, connected just to a sheet metal screw on the aluminum flashing. Just get a drill, poke it in there, put in the screw, use the leads of the conductor, and you're good to go. So that's way cheaper than buying special hardware. Another thing you can do is use a pair of 3-wire N0AX, the UF, which is direct burial. You can use the 3 and the 3. That's only 6 wires, but they're very heavy wires. And you can put the motor start capacitor out at the tower. And so that saves you another pair of wires coming back to the shack. So, but copper is expensive these days. I'm not sure it's going to save you any money. This is a lot less expensive than the fancy rotator cable. You save that for going up the tower and rotator loops and inside your station. Okay, let's go back to the perimeter ground. Here's the perimeter ground. It's got a ground rod. The ground rods are all connected together with heavy wire, like number 6 AWG. Number 6, number 6, number 6. All of these ground systems, your AC safety, your telephone, your cable TV, that antenna that you put on the roof that has the ground wire that NEC requires, and that all goes down to a ground rod. You've got to bond all of these connections together. The NEC is unequivocal on this. They use the word shall. And if you've ever done any contracting, you know the word is shall, is no wiggle room. This is the way it's got to be. And the NEC says all external ground electrodes shall be bonded together. And the reason that is if you have a big lightning surge that flows through the earth, if you measure what the resistance is between those ground rods, you might measure 10 ohms, 20 ohms, 50 ohms, 100 ohms. And so what do you get between those two ground terminals if you say you had 1,000 amp lightning surge through the earth? That's no big deal. That's not even a really large lightning surge. If you have 1,000 amps flowing through, say, 10 ohms, you've got 10,000 volts between this point and this point, just because these things are only connected together with dirt. The conductivity of dirt is not very good. So that's why you replace it with a bonded wire. Typically it's buried, so it's in contact with the dirt, but you want the minimum amount of voltage between these different ground terminals. You want your AC safety, your phone, your data, all that stuff, all going up and down together. They won't be at 0 volts, but you don't want really high voltage between your different systems. And that voltage difference is what causes a lot of damage. So when you're sitting there, you hear these stories all the time. Thunderstorm rolled through. I left the shack. I was in there watching TV, and all of a sudden I saw the flash and this big green arc jump from my computer to my entertainment system. And now nothing in the house works. Why is that? Because the ground systems, the ground electrodes, were not bonded together. And so when the lightning flowed through the dirt, it created this really high voltage between point A and point B. And high voltage between point A and point B causes current to flow. And the current is what does the damage. So your perimeter ground system is a bunch of ground rods all tied together with a heavy conductor. And everything is tied to that outside. And you don't want to create these low impedance paths through your station. We mentioned this before. Here's your tower, has an antenna on it. Okay, here's your feed lines. They come over to this dandy entry panel that you made. It's got a ground rod, and it's connected to your radios. Okay, so here comes the lightning. Lightning says, ah, great, a ground terminal called an antenna tower. So it hits the tower or it hits something close to the tower. Lots of current going through the tower, through your feed line, gets over here, and it says, oh, I've got 2 paths here. One goes to the earth. I like that one. Okay. But here's this other path to the earth, and it goes through the feed lines, through your radio stuff, down into the power supply and the AC branch circuit, over to your service entry, and down to that ground rod. Well, this is a destructive path. You want to give lightning lots of other options that do not involve this path right here. So what you do is you have your external perimeter ground system. Okay, so this time the lightning comes in on the AC line. Very common. Okay, it comes down to your AC service entry. It says, oh, here's a really good external ground system. I've got my perimeter ground, ground rod, ground rod, ground rod. You really build up your shoulder muscles pounding in these ground rods. And if you've got a rocky installation or something like that, the NEC allows you to bury it in a horizontal trench or drive it in at an angle. It doesn't have to be vertical. Okay, so here's the unprotected AC line, and you ran that all the way over to your entry level single point ground panel, and you've got a surge protector on it. So the lightning, even if it gets all the way over here, has another very attractive path outside to another ground electrode. So lightning current is no different than any other current. It wants to take the path of least resistance. So give it all these paths of least resistance outside your house. Lots of bonded ground electrodes outside the house, and they should go around the house. Don't go through the station, don't go through the house, don't go through the basement, don't go through the attic, all that kind of stuff outside. You got your tower out here. We've seen this in the handbook for years and years. You're looking down Roan 25 or 45 or whatever. You got this nice concrete tower base here, and you followed the handbook directions, and you put a ground rod out here for each one of the tower legs, and you connected it together with this nice big ground ring of wire. Okay, Well, as long as you got the guy with the backhoe out there, have him or her dig another 30 feet of trench. It doesn't have to be 6 feet. It doesn't have to be real destructive. And put some radial wire, heavy radial wire in that trench with ground rods. And do that on each one of the tower legs. When you talk to the cellular radio guys and you talk to them about the grounding their towers and what do they do when they're up on a hill and there's rocks and stuff, they say, we put out radials. We get a lot more protection out of the radials than we do out of the big concrete base that goes down into the dirt or the rock. So put out radials, connect them solidly to the ground ring around your tower, and that'll pay off big benefits. You also, on the tower, you want to bond your feed lines to the tower every 50 feet. Yes, it's a pain in the neck. If you're running hardline, there are ground kits for stripping back some of the plastic jacket, and then you put a little clamp around the outside shield, and you bond that to the tower, and then you weatherproof it with mastic and electrical tape. You can do the same with regular coax like RG213 or whatever. You buy one of these brackets, DX Engineering sells them, others sell them. They have the right size holes for in connectors and for PL259s. Yes, you have to cut the cable. You have to install 2 more connectors. Yes, you have to weatherproof them. Yes, it's a pain in the neck. But if you don't, remember that number 12 wire that had the lightning current flow through it, and it had 761 volts from end to end. A typical tower can develop, and when hit by lightning, 100,000 volts between the top and the bottom. It's not uncommon. And if you don't have your cables bonded to the tower, there will be 100,000 volts between the cable shield and the tower. And that's when you blow up your cables, you get pinholes and splits and all sorts of other nasty things. So unless you like troubleshooting and replacing cables, make sure you bond the cables to the tower every 50 feet. If you have an insulated base tower, put a spark gap down there. It can be as simple as a pair of heavy wires crossing each other, but just a little bit apart so that when there's high voltage, it will jump across that little gap. It's just like gapping a spark plug. For those of you over a certain age, I know you've installed the spark plugs and set the gap just to a few mils or whatever. About 0.03 or something like that is fine. You want to figure out what the highest voltage that you're going to apply to the tower will be. Give yourself a little safety margin and then set the gap for that amount of voltage. I typically counsel people to have them cross like this and not like this or like this. If they are parallel, what you get is debris in them or insect nests, and rain. And if you put them like this, there's no real incentive. There's a very small gap, and insects and rain and stuff don't collect in them. Okay, let's jump over to RF management. This is the third of the types of requirements that hams have to deal with. First thing we have to realize is even though our antennas per se are outside and they're up in the trees or they're up in a tower or something like that, you're still very, very close to your antenna system. So you're going to have high field strength in the station. And everything in the station that's metal is an antenna. It just is. And that includes your feed lines, your panels, your AC lines, your safety ground, your interface cables, your mic cable, the coax jumper, all this stuff. It's going to act as a big antenna to collect RF energy. So what are we going to do with it? Okay, one, we forget about trying to create a magic all-band RF ground, the magic 0 volts. Well, if I just connect to this point, it'll be at 0 volts. I won't have any problems. Forget about it. Okay, and concentrate instead on bonding everything together. So you have 0 volts between pieces of equipment, and everything goes up and down together. Keep your connections electrically short. not big loops of wire. Don't coil up your connections, all this stuff. If you can connect stuff with a simple little strap to a pipe or your bonding plane or whatever, you're in much better shape than if you have wires running all over in the back of your equipment. The goal is to keep everything at the same voltage with low inductance, electrically short connections. You install an amplifier, you're going to have even higher field strength. Not only are you going to meet the neighbors, you're going to light up everything in your station too. So that's going to require extra attention to bonding. One thing that you can do, and we've all seen the picture of the copper pipe in the back, and I'll get to that. If you can create a common reference plane, remember that piece of aluminum flashing that was in my tower base single point ground panel. Well, you can use that same flashing and you can lay it out on a wooden desk or table, and you can use that as a bonding surface, and you connect things to that. But this is typical, more typical. You've seen this in the handbook and the ARL documentation for many years. Here's the ARL ID in the current handbook. We use a big piece of copper pipe. We use 1/2 inch because it's the cheapest possible thing we can get. And we're hams, so we're cheap, okay? So we just got a 1/2 inch pipe there. We screwed it down in the back of the desk and we connect everything to it. Okay, what you need to do is use ground clamps. Well, a lot of us use, and I did too, we used hose clamps, okay? The stainless steel hose clamps. They are not made for metal to metal connections. They're made for flexible, holding something flexible like rubber, a hose, to something incompressible like metal. If you put a hose clamp on metal to metal stuff and you tighten it up, okay, and you come back next day or two, you'll be surprised how much it loosens up, and it will thermal cycle and loosen up over time. So use a real ground clamp. A 1/2 inch pipe is just as big as a 1/2 inch ground rod, and that works better. It's more expensive than a hose clamp, but it works better. Another thing you can do is sheet metal screws and terminals. One thing I've started to use, and I don't think I have a picture of this, is the ground bars that you buy for AC service entry panels. If you open up the panel and you take off the protective thing, you will see these big bars over at the side of the box where the neutral wires and the ground wires go. You can buy smaller versions of that for a few bucks at the hardware store. 5, 7, 9, weird numbers, 13, 29, I don't know. Take one of those and bolt it to your desk on that piece of aluminum flashing, and it's perfect for grounding and all your ground connections from your equipment. But by doing this bonding, however you do it, you eliminate these hot spots when you have your equipment sort of arranged on the desk and stuff. And on 15 meters, you know you're going to get bit on one band, for example, because it's hot on that particular band. By bonding everything together and keeping everything the same voltage, you eliminate a hotspot. Hotspot is a point at which it has higher voltage. So bond them together, get rid of the hotspots. It also reduces the buzz and the hum in your low-level audio that you use for FT8 or whatever, voice, what have you. It just reduces the buzz and hum because there's less voltage, and that means less current getting to where it should not be. It also means you don't have to move equipment around to operate on certain bands. Everything is kind of bolted together electrically. So it's all at the same voltage, goes up and down together. And you also want to bond your station to the entry panel. Some people run an actual separate ground conductor, or you can use the feed lines. And NEC says that's okay too. All the shields of your feed line also act as bonding conductors too. Inside, however you have your bonding structure, here's the example with the pipe. You minimize loop area and cable length of all the cables that are connecting all the different little boxes together. You minimize area. The amount of voltage that's induced in a loop is directly proportional to area. So if you make the area small, you also make the voltage that causes current to flow in the loop small. Minimize the cable length, minimize your loop area. Use the shortest cables you can, and you can coil them up. And it was pointed out to me that if you coil them in a figure 8, like this, instead of this, a figure 8, this part of the coil cancels with this part of the coil. So you can minimize your inductance and coil it up at the same time. Here's your bonding bus or your reference plane, whatever you use, low impedance, electrically short connection. And you always want to use shielded cables for audio, control, all that stuff. The only thing that's unshielded should be your power, your 12 volts, and that should be well bypassed at the equipment. Use the shielded cables, the USB cables. I like Triplite. They're not expensive, they're high quality, and if you've got metal enclosures, it will act as a kind of a bonding connector for your USB stuff. And that also helps it eliminate radiation from the data signals in the cable. It also helps you prevent RF from getting into the data signals that are in the cable. Shielded USB cables are important. Same for audio. Use these short straps or wires as we talked about before. Here's an example. Here's a station. This is my old station setup. I had a Costco banquet table here. I put a piece of aluminum flashing on each end. I just took a drill and put sheet metal screws in it on each end and held it down. You can see a copper pipe in the back, and all of my cables lay on that surface. And that surface, when the RF comes in, that surface helps minimize, it sort of shorts out the field and minimizes voltage across that desk. And so that also minimizes the pickup of the cables. So anyway, it's not expensive. It's not hard to do. Here's some examples. I do have a picture of it. Here's one of the ground bars that I bought. Typically, this would go in an AC service panel. And here I'm putting together a new table for the station. And so I got my aluminum flashing, and I cut it with a razor blade, one of those utility knives, and I screwed it onto the table using these things called lath screws that have a real nice smooth head. And then I bolted this onto the table. There's one at each end. There's one over here, one over here. And each one has a sheet metal screw. It has a stainless steel washer, and it has an external tooth lock washer. You want to use external or internal tooth lock washers so they bite into the aluminum flashing and they bite into the ground bar. If you use split O, it works mechanically, but it doesn't maintain that really good connection. So you want a lock washer here. This is my connection that goes to the perimeter ground system. And you want this all tied together so that thermal cycling doesn't cause your system to kind of loosen up. You don't want to have to go through and tighten all your ground connections every so often. Buy a big box of lock washers and you'll be good to go. Okay, let's back up and do a ground system review. I'm almost done. Yay! Okay, a single solid ground system. Notice that I haven't talked about, oh, this is the AC connection. This is the lightning protection. This is the RF. They're all the same stuff. A single solid ground system. Short and heavy and direct connections, they make everybody happy. It's good for AC safety. It's good for lightning protection. It's good for RF management and clean audio and all that kind of stuff. Doesn't do anything about bad breath, but you know, whatever. And so you want to bond all of your grounds together. You want to keep your protectors together. Why? So they all fire at the same time and everybody's going up and down together. I can't stress that enough. Particularly if you're in a second floor or upper floor station, you got to just kind of pretend you're an airplane and everything is just going to go up and down together. You don't know what the voltage is, but you know it's going to be the same, and that's the important thing. And your perimeter ground is outside the building, and give lightning what it wants, which is heavy direct paths to the earth so that all of the current disperses or it comes into your ground system and goes up to the cloud outside the building. That's so important. Here are some additional resources. As I said, I will send Paul a PDF of this. Here's your professional associations and companies. This is all really good stuff. Mike Holt Enterprises. Mike is a former electrician and now he trains electricians, and he has this big website, and there's a lot of good stuff on there that's available. A lot of training and tutorials and all this kind of stuff. And Polyphaser was originally by the Block brothers, and they are hams today. So if you go to this website and look at the white papers, there's papers and tutorials on lightning protections for communication facilities, and there's some stuff written specifically for ham stations. Here are the standards that I use and to refer to in my book. This is called the R56 standard. It's from Motorola. It's available online as a PDF, and basically it's for communication facilities that operate at VHF and up. The FAA document is how they build their HF systems, and so there's a lot of HF know-how in there. IEEE standard 1100, that's the AC power system standard. It's an expensive book, but you can get it through the library if you're really interested. But this one, you paid for it. It's free. Mill Handbook 419A. This is the military document that says how they build HF communication sites. And if you want to know how they do it, it's all in this book right here. You don't have their budget, that's for sure, but you can look at it and you can say, okay, I kind of get what they're doing here. I'll do something similar within my abilities and resources in my station. There's some good books out there. Ron Block, here he is, The Grounds, and he's got his new book that I showed you right here. If I can pull this out of the stack. Lightning Protection, good book. K.A. Rand, also a Polyphaser book. And the ARL Technical Information Service is so unappreciated by hams. You can go to the technology tab on the homepage and start following this stuff through. There's a tremendous amount of information there, and a lot of it is available to the public. I know most of you are ARL members. That's a definite member benefit. Electrical safety, go to that page and you get a whole bunch of stuff on electrical safety, grounding, and lightning protection. Articles, all sorts of stuff. Ron Block's 2002 QST articles are in this tab right here. So all good stuff. So I will send these slides to Paul, and I'd be happy to take questions if you're not totally glazed over. At this point, it's been a bit of a fire hose. I go real fast, but if you've got questions, I'll try to answer them right now. So I'll let Paul be the MC on that.
Thank you very much. Very good, Ward. Hey, do you still have those pictures of the? I had some people asking me how we grounded the dish antenna, and I sent you some pictures. Do you still have those?
Maybe somewhere. I don't know. I couldn't tell you. I save everything. Google Mail might be able to find it. But
Yeah, I had pictures of our the way we had grounded the dish was we did that exothermic stuff.
oh yeah, that's right. CAD welding.
CAD welding. There you go.
If you guys like fireworks, and I know we all like fireworks, CAD welding is so cool. Yeah, ask Paul to show you his pictures of it. You put that wire in the crucible and the magic powder in there, and you light it off, and a couple of seconds later, you have a ball of 2000-degree metal, and it's all welded together. You can bury that connection. You'll never have to look at it again. It's not that expensive. It's about, I don't know, $7 to $12 per shot, depending on how big your ground rod is, how many wires you have coming into the crucible, all that stuff. A lot of YouTube video on that.
Yeah, that's for sure. I've got to remember where the where I put those pictures, but
Yeah, me too.
we're all in the same boat, I'm afraid. But
You bet.
anyway, there I can bring those things up and show you at some point how we did this. But we used the 4/0 wire around the perimeter of the pedestal, which holds the 60-foot dish,
Yep.
and we use that CAD welding to weld that 4/0 wire to these ground rods, the solid ground rods that that the electrician put in for us, because we were just too lazy to pound them in, and we and then we connected that all, of course, to the superstructure that was holding up the dish and everything else. So when
Yeah.
lightning hits the top of the dish, or the top of the feed rather, when it's in its bird bath position, it goes straight all the way down. We have a single ground rod going all the way, ground wire running from the feed point of the dish all the way down to the base. So
You bet. Have you ever seen an installation called Lightning Field?
no.
You ever heard of it? It's sort of one of these art installations. It's in New Mexico, and it's in a pretty remote spot. But it's a whole field of large steel poles that stick up. They're about, I guess, about 20 feet long, and they're about 30 feet apart. And there must be a couple, 300 of them, and they're in this big grid, and it's all well grounded. And what happens is the thunderstorms move through, and they just nail this thing. And there's like a bunker or something that you can watch this from a safe distance away. And you can just watch the lightning hit these things. So they could go to any ham station and get the same effect, with the towers. But yeah, if you're dealing with big structures, yeah, you got to be dealing with big wire. That's expensive, so typically hams don't deal with that. Other questions?
So I have one more question here, since I've got the floor. So the pedestal is well grounded, and then we have feed lines running underground through plastic pipes all the way over to our building, which is 120 feet away. And we were thinking of, or we are in the process of grounding the building itself by using ground rods along the front of the building, where we've got some metal pipes going up, and we're going to exothermic or CAD weld the wire from the ground rod to the building, so that if lightning hits the building, it will go straight down to ground rather than going around us. At least that's the theory. And then we're also going
plan.
yeah, and then we're going to put ground rods around the building now, and then hook those up to the building as well as to the racks that we have inside the building, so that all of our racks are going to be hopefully the same potential. But the only thing is, do I need a wire? Do I need to run the 4/0 from the pedestal, the 120 feet over to the building, or
yeah, I get this question all the time. My tower's X feet away from the house. I've got a ground system at the tower, I've got a ground system at the house. Do I need to bond those together? And the sources aren't all in agreement. There isn't a hard, if it's greater than this distance, no. If it's less than, yes. Typically, The military bonds stuff up to 200 feet separation, and they use a really big buried copper strap. It's expensive, and they tie it all together. For ham stuff, I tell people if it's more than 50 feet, you've got so much inductance in the ground system that at RF and for most of lightning, it's not very effective. But if you bury the wire and it's a bare wire, then you've got another big radial in the ground that acts as a conduit for charge to, disperse into the earth. So it doesn't hurt anything. The NEC allows you to use feed lines from a tower to a facility as your ground connection. Coaxial cable shields are pretty heavy. You have to ensure there's at least one connected all the time. And you have a variety of different connections, but they're all in parallel. For hams, I say, what's your budget for copper? And if you want to run a nice heavy copper wire in the ground, it doesn't do you any good if it's in the conduit, then go ahead and bond them together. If you've got the power that's close to the house and you have radials, and yeah, you can bond the radials to your perimeter ground system as well.
Well, that's good.
Thanks, Paul, for asking that.
Hey, Ward, just I'm a big proponent of perimeter ground. I want to give a quick story. First of all, the perimeter ground consists of 8-foot ground rods about every 20 feet apart. They say to separate them at least twice the length of the ground rod. Is that what your understanding is?
Yep. Yeah. If they're 8-foot ground rods, you put them 16 feet apart.
Right.
16 to 20 is fine.
Well, I did it 20 feet apart, and came around to the start point. It took weeks and weeks to do that, manually driving the ground rods down. Came down to the last ground. I had the wire in my hand, sunny day, and about 20 miles away from me, there's a lightning strike. Me holding the wire that has been grounded around like through maybe 9 or 10 or maybe more ground rods. I still got a tremendous shock. Apparently the lightning strike was induced into my 80-foot tower, and it was then dissipated through all the ground rods, but there was enough at the end of that wire to give me a tremendous shock.
Yeah.
This system's been in place for 10 years. I've got 2 towers now, 90-footer and an 80-footer. A lot of HF Yagis, a lot of coax coming in the building through a ground box. About everything is ground to the box and connect to the perimeter ground. I never disconnect antennas. I have nearby lightning strikes. I've never lost one piece of equipment.
There you go. Well,
it works, but it's a lot of work to get it in.
It is. It absolutely is. The magnetic field from a big lightning strike can be enormous, and it's an inductive coupling between what is essentially one big long straight conductor where the strike is, and whatever else, what other conductors are within miles of the strike can pick up significant energy. So, and thanks for the contact on meteor scatter.
Yeah, I was going to say thank you for it also. That was a surprise. It was a fun time. I made 115 contacts.
Well, that's a lot.
85 on 6 and another 30 on 10. Good to hear so many new guys who had never worked it before. Some calls I'd never heard locally. I heard a bunch of new guys. So it was good to, that Hamsci group did a good job. The big one will be in the Leonids in November. So this is sort of a test for the Leonids. There was a lot of E-skip mixed in that messed things up a bit, but it was a fun contest.
Oh, it was totally cool sitting there watching propagation, and it would go from sporadic E to airplane scatter. I'm not far from the airport. Then there'd be some tropo, and then there would be a meteor ping. Right. And it's kind of hard to, I just worked people, I didn't care, whatever, Yeah. So anyway, yeah, that's fun. Yeah, you can get significant amount of energy from a nearby strike, and that's why you want to put the effort into the ground system.
And by the way, my house My house ground, the AC ground is on the east side of the house. The shack ground's on the north side of the house. And the tower, the first tower I put up, the house bracketed tower, is on the west side of the house. They're all tied to the perimeter ground. They're all at the same potential.
There you go. Whatever that is. Yeah. Okay. Thanks. Thanks, Rich. Any other questions or comments?
Yeah, hey Ward, Barry, W2UP. You hear me okay?
I can hear you fine. You're blasting through.
Good. Yeah, I'm using a different computer than usual, and being a CW guy, I didn't have a microphone handy, so I had to go find one.
Yeah.
Anyway, question about the lightning arresters. Anecdotally, a year or two ago, I bought a polyphaser and it was shorted. So I, went back to HRO, got my money back, and started doing some research online. Anyway, so what I found is there are basically three companies: Polyphaser, and an interesting thing about that is I noticed they're now made in China, Alpha Delta, and then there's MGS, not MGS, Morgan Systems, which
Yeah.
took over from ICE, I believe. So I wonder if you can comment on the different companies that make these things and their quality.
Well, they're all pretty good. Alpha Delta obviously sells a lot to the amateur market, but they have significant presence in commercial. Morgan is a kind of a step up market-wise from hams, and Polyphaser's the gold standard. And if you look in the various boxes, you can see that they have slightly different techniques for assembling these things. I would say most hams would be just fine with Alpha Delta. It's not, I wouldn't expect gross differences in performances. One thing I can say is it's good to have the type of arresters that have the little unscrewable cap, so you can take the cap off and then visually inspect the gas discharge tube cartridge. And if they're the clear glass kind, you can use a microscope or you can use a magnifying glass. And if you see damage to the electrodes, like pitting or some kind of like a buildup of material, then it's been compromised and you need to replace it. If there's any scorch marks, that kind of thing, you need to replace it. And you can buy a box of these things. They're not that expensive. Just make sure the mount is clean and that you don't force the gas discharge to the cap in there too hard. You want it to be firm, but not terribly hard. There's also two different kinds of arresters. One is a straight through, where the connection between input and output is a direct wire, and the gas discharge tube is pressed against the wire and goes from there to the enclosure of the arrestor. You can use those on coax lines that have that are powering preamps or other such things. And there's also a kind that has a series capacitor between the gas discharge tube and the input side. So it has an input and an output side. And that capacitor is there to put a little bit of reactance in the line so that this pulse causes the voltage to go up faster. And when it goes up faster, it gets to the breakover voltage of the gas discharge tube faster, and it clamps the transient faster. So if you're not going to be powering anything through these arresters, then go ahead and use the capacitor block. If you are going to be using preamps or something, or you think you might, you have to use the straight through ones. But I would say all three brands are fine for amateur use.
Okay, so you think my polyphaser experience was just a fluke and not that
Probably.
the quality went down because they're now made in China?
Yeah, I have no idea. There's been so much change in manufacturing, and it's going on. Obviously, it's going on right now for all kinds of reasons. I would simply check when you get it.
Hey, Ward, a comment regarding the GDT.
Go ahead.
Not all GDTs are the same. Some will arc at at 75 volts. You have 100 or 150 volt ones. Depending on the
Yes.
power rating, if you're running a kilowatt, you're not you're going to arc through 75 volt one. You're going to develop enough voltage even across a 50 ohm load to probably arc through that. So you got to make sure you're getting a gas discharge tube of the proper voltage, the breakdown voltage.
Yes. There is a power rating for the arresters, and that's what it is. It's the rating of the gas discharge tube. If you can't really check gas discharge tubes with home equipment, but if you really want to check one, you can take it to a motor rewind shop. They typically have a high pot, meaning high potential tester, and you give them the part number of the gas discharge tube, look up the breakover voltage, and then they will run the voltage up to the point where suddenly it starts conducting current, and they'll tell you whether it's good or not. But these things are not expensive. They're typically under $2. And so you just buy a box of them, have them around, and once a year go inspect them. And if anything looks out of order, throw them out, put in a new one.
Thanks.
You
Hi,
bet.
Ward and Bruce Schober, KO4 PRE. I'm putting in a tower, and it's right next to a metal building. It's got sheet metal siding and a roof on it. What kind of concerns and issues could I have with that in the electrical fields, from my antennas?
Well, I mean, from the standpoint of grounding and bonding, depending on the code where you are, I think they require a ground electrode for the siding. And typically the roof is one set of panels that are bonded together. And then the horizontal stuff is what's on the horizontals. It's not really horizontal, it's the walls. Okay, so the roof is one section, the walls are another. And you should tie both of them to a ground in case there's a lightning strike or something. But in terms of trying to bond all that together for RF purposes, that's kind of a non-starter. The sheet metal screws that hold everything together, they do a reasonably good job of bonding at first, but as the siding ages, that will oxidize, and there's really no way to guarantee all that stuff's going to be bonded. As far as electrical interaction with the tower, it's just another big conductor out there. You might want to tie the tower ground and the ground for the building, if there is one, together, bonded outside somewhere.
Okay, thank you.
Well, Paul, I think we ran them out.
This is Steve, Kilo Charlie 1, Kilo Echo Zulu. Can you hear me?
I sure can.
Okay, great. Ward, I have one question here. Our AC electrical panel is grounded to the external cold water feed pipe that comes in through the basement concrete foundation. I have 5 other external ground rods driven into the ground around the property, which I'm going to bond together with a buried number 4 copper wire. But how do I bond it to the cold water feed pipe? Like,
Okay.
have to
First,
excavate to find the feed pipe? I guess so.
well, I'm going to back up and make an observation first. How old's your house?
80 years.
Okay. Back in the day, that was a perfectly good solution, and it still can be. But I want to caution everybody who thinks that they have a big copper pipe outside. If your house has ever been serviced with a new feed line or anything like that, a lot of the times they've taken away the metal that went to the main water main, and replace it with plastic. I've seen pictures of installations where you've got a perfectly good metal pipe that goes through the concrete wall, and then about a foot outside the wall, it changes to plastic because they redid the water service X years ago. Everything outside is plastic now. Okay, if you're absolutely sure that you've got metal outside and that it's in good shape, then what I would do is I would run a bonding wire from your perimeter ground system through the wall and attach it directly to the wire that's connected to your AC service panel, right where it connects to the cold water pipe. You follow me on that?
Yep.
Yeah, that's what I would do. And then you're not messing with your plumbing. You're not making any assumptions about the plumbing. And another thing is, in the house, all it takes is one little plastic coupling somewhere, and your plumbing system is no longer all metal. So, you know, over the years, things get done to house plumbing. And I'd just be real cautious about using plumbing as an electrical ground. If it's working for you, that's fine. But what I would do is run a wire from your perimeter ground inside the house and connect it either directly to the service panel or to the point at which the service panel connects to the ground. And I would also ask a local electrician if that meets code.
Okay. All right. And I have one other question, and that is, my station is a POTUS soda station. Okay. And I operate outside, not typically in a vehicle. And I have wondered whether I should establish a ground system, you know, when I'm out in the field. And if so, I mean, I have an extra 8-foot copper clad steel ground rod that I can bring with me, but I don't know if that is sufficient. And one of my colleagues said, well, your counterpoise for the antenna services as a ground. And I said, I don't think so, not an electrical ground.
Well, I wouldn't. Okay, you're running from a battery or a generator, I assume, when you're out.
From a battery, a LiPo that's augmented with a solar panel.
Right. Okay. So this system is totally floating from the earth, which is perfectly fine. And you don't need a ground rod. I wouldn't even think about it. I mean, there's really no way to protect a portable station that you're going to put up and down in a few hours from lightning or anything else. If you want to do a ground system, now whether it's a counterpoise or whether it's a, you know, one thing that works well for me when I'm out portable is just to take some rolls of chicken wire and 10-foot rolls and just lay them out on the ground and use the split nuts to make contact between the rolls and then to the feed point. That works terrifically at RF. But as far as lightning and AC safety, as they say in the Northwest, forget about it. Okay. You know, it's just not happening. If there's any lightning in the vicinity, just lower stuff and beat a hasty retreat. But you do not need a earth electrode. The antenna system will be happier if you can put out radials or the rolls of mesh or whatever, or even just a counterpoise wire. But you know, it's not a quote ground system unquote.
Yeah. All right. Great. Thank you so much.
You bet.
It's AA4Q. Can you hear me?
I can. Go ahead.
Thanks. Okay. I have a similar situation where I'm operating field day or some other portable situation, except I'm not worried about lightning because I am going to pack everything up if there's lightning. But I have RFI getting into the laptop and the other associated things hooked up to the laptop. How do I bond the laptop, which has a plastic case, to everything else? I'm kind of fantasizing about how I can, on the rack where my radio is, I can put one of those ground terminal strips and ground everything to it except the laptop.
Okay. what I would do is, it's a magic thing for field day and portable operations. Take a roll of aluminum foil out and lay it on the operating surface. And that makes a nice little reference plane, and you can clip your portable rack. You can probably see a little portable rack right here. I do that also. And for the laptop, if you're getting RF into the laptop, I think the best thing for you is Clampon type 31 ferrites with wind all of your data and power cables on that. I've had problems with mice and with keyboards, and some are, more susceptible to others. You may have to experiment. But if you've got a laptop, I guess you probably have like a touchpad or something like that. The only place you can get to a ground on the laptops is wherever the video cable attaches. There's usually a grounded screw, or like one of those little hex spacer things, or the HDMI, the actual shield of the connector will be available. But it typically doesn't buy you anything to try and ground a laptop. They're not made for it. Try to create the reference plane with the aluminum foil, clip everything to that, and put the ferrites on the cables that go to the laptop, and that's probably about the best you can do.
I've got a ton of ferrites on it. Go ahead.
A suggestion: add a quarter wave, electrical quarter wave of wire connected to your radio, and extend it outward to bring the high impedance point to the end of the wire, and it'll it's a fake ground. You see these
Yep.
What do they call those imitation grounds?
Virtual grounds.
Virtual grounds. Yeah. You do that, but a quarter wave at the operating frequency, it gets the RF
At
away
all
from
of
the radio,
and
may improve the problem.
Keep the end of the wire, the open end of the wire, keep it away from your bare feet.
Right.
Don't ask me how I know that either. But yeah,
it'll be hot at the end of that wire.
I would just have a bag with a 20 meter, a 15 meter, a 10 meter, each band that you operate have a little quarter wave piece of wire with an alligator clip on the end. And whatever piece of equipment is getting screwed up, clip that alligator clip to that piece of equipment and stretch the wire out and keep kind of keep it away by itself. And it's sort of like balancing a tire. You're just putting an electrical weight on your system to damp out a vibration there. But that will create a low impedance point at the alligator clip. Good point, Rich. Go ahead, Peter.
Yeah, Ward, thanks for a very interesting presentation. I have another question, and this is somewhat related. I think it was to Steve. He was asking, he said his house was 80 years old. A lot of homes have only 100 amp service, at least were built with only 100 amp service. And now we have so many electronic things, such as electric cars getting charged, electric heat pumps, air conditioning, et cetera, et cetera. What should be the minimum amount, in your view, of the amperage of a home today, if you're running a ham shack with those sort of tools, those other kinds of equipment around?
New construction is a minimum of 200 amp. That's typically set by the local building codes.
Yes, 200 is typical now, but a lot of people have 100. In the 70s and 80s, a lot of homes are built with 100 amp service.
Yeah,
in Canada.
My house, and I have a rural UTH where the main station is, where the towers are. And it originally had 100 amp service. And, when they, a few years ago, I don't know when, they replaced the box with the big service. The original box is still downstairs somewhere. So, yeah.
So your service people did that automatically. You didn't have to call them. Because one of my colleagues, who is actually an electrical engineer, he happened to be home when he was charging his car and running a few other things, and his electric box caught fire.
Oh, I'll bet. Yeah. Oof, that's a lot.
And he had 100 amp service, and his house is built in the late 70s.
One thing that people do, and this is not a bad idea. It's not a ham radio thing, but once a year, go through and tighten all of the connections on your circuit breakers, wiggle the circuit breakers, you know, wiggle, tighten that hot wire in there with a very insulated screwdriver, or, you know, turn it off, whatever, and just make sure you've got tight connections. Another thing you can look at now is these infrared cameras. And while you're running the furnace or the air conditioner or what have you, take a look with an infrared camera and see if there's any hot spots. And if you find a hot spot, fix it.
Good advice. Thanks a lot. I enjoyed your presentation.
We do that in industry quite often. That's part of our preventative maintenance for our electrical bus bars in the factory.
I don't know anybody.
We do it every year.
A friend of mine gave me a Henry 4K, and I'm like, oh my God, what am I going to do with this? You know, maybe I'll fire it up once or twice and see if they can hear me on 75 meters. But, you know, it's hams don't typically draw that much current. But now we're talking about electric vehicles, and you've got all these services in the home. It's much more demanding. I'll put it that way.
Yeah. And sometimes we don't think about that in terms of our basic service.
Yeah, that's right. Yeah. Well,
Hey, Paul
anyway,
and Ward, will this presentation be available for
have to ask
viewing as
Paul.
for a ham club?
I'm recording
Maybe
it
not.
actually, so it'll be on our regular YouTube channel for Front Range 6-meter group.
So you had
There
no
you go.
problem of me playing that whole thing back at a club meeting?
No problem at all. It's not copy
Very good.
protected or anything, but just
Please
make
do.
sure you mention Front Range 6-meter group.
Of course, of course.
This
There
is
you go.
the I just showed you the
There it is.
picture of around our pedestal, and that's the number the 4/aught wire running around, and I have another picture of which would give you a little closer view of the this is the
There it is. Yeah.
that's the weld that we did with this CAD weld, and you can see where the wire and the copper pipe were, you know, obviously
Thermite
together.
weld. Yep.
Yeah, and so we've got 6 of those around the perimeter of the pedestal. I'm not sure how many feet that is, but it's quite a bit, and they're about 6 feet away from the sides of the pedestal itself. So it's
Yeah. One of these things is a cup of, it's typically about an inch, maybe inch and a half in diameter, and maybe about 2 to 3 inches long, depending on the size. And so it's got a little grommet at the bottom. So you slide it on the ground rod, the grommet seals it on the bottom, and then it's got brass eyelets, and you cut the ground rod and you put that through the middle so that it's touching the ground rod. And then you hold it all together and you pour in the thermite, which is the coarse stuff. That's the real stuff.
Yeah.
And then you put a little shield on, and then you put this lighting powder on the top. If it's a windy day, make sure that you shield the whole assembly, because that lighting powder will blow away. Don't ask me how I know that either. And so then you can put a lid on the top, another ceramic lid, and you light it with either one of those sparking tools, or a sparkler will work. And then you, as they say in the fireworks industry, what do they, place on ground, retire quickly. You just back up. You know, it doesn't spark or anything, but boy, it gets hot.
Yeah, the electricians were afraid of getting too close to it. I had all this done professionally, by the way, and in order for them to light it, they actually took some wire and some AC wire, and they hooked one to the ground rod and one to the powder, and they turned on 120 volts to it.
Well, that's a spark. Yeah.
I've never seen them done like
work.
that, but I got a video of that, and it was really funny to see that happen.
If you buy a box of those things, and you don't use them right away like most of us do, make sure you keep them in a very dry place because they're somewhat hygroscopic. I put them all in a sealed Ziploc plastic bag inside another bag for the whole box, and then try to keep that someplace where it's not damp. Anyway, so there you go. Paul, I will send you
I'll
the
let you.
PDFs.
Yes, thank you.
Have at it. So guys, thanks very much. I'm gonna
Great
pull the
job
plug.
there.
It's 10 o'clock and I will see you on the air.
Thanks again.
All right.
Great.
Thanks a
Thanks,
lot,
Ward.
Ward, and everybody else.
Okay,
Appreciate it.
73 guys. See you on 16.
73s. Yep,
73.
definitely.
Good night, everybody.
Thank you.
Hey, Paul.
Thanks, Paul.
Yeah.
How deep is that ground wire around the pedestal? 6 inches?
It's probably trenched down maybe, yeah, 6 or 8 inches, something like that.
Excellent. Thank you.
And the rods are approximately 8 to 10 foot themselves.
Yeah, I wanna do that around the base of the tower.
Yeah, if you go on eBay, you can get those the Cadwell options depending on what size wire you're going to be using. We got one that it was donated to us actually, and there's a little sparker thing that you can put in there and click it. That comes in the Cadwell stuff comes in little. You can get a little package of them, and they're all prepackaged, and you just drop them in there, or you can get them in a container. And you just put a couple of spoonfuls of that stuff in there. You make sure, like, because the the mold is made of graphite, and it goes around the ground rod itself at the bottom, so that it doesn't allow the powder to fall at the bottom. You just fill it up, and then there's a little peak hole at the top there where you can put in your lighter, and when it goes off, it's pretty nice. It's like a sparkler, and it looks like this when it's done, and you can see how it kind of melts itself to the 2 pieces of metal there. But if you go on, if you just Google CAD welding, there's all kinds of videos on it. So
Yeah, I've seen several of them already.
if you have
pretty
any questions
interesting.
on it, you can always call me, and I can give you more information on what we're doing, because we're going to try to make sure that
Awesome.
we've got a really, because the trouble is, if you bury something and you put one of those mechanical clamps on there, it corrodes over time just from the soil's acidity and everything else. And then you have to dig it all up again and then clean it off and then bury it again. So it's this way, you don't have to maintain it over 30 or 40 years.
Right. That's my goal. Thank you.
Awesome, guys. All righty. I'll let you guys run. I hope you had a good time, and we'll see you
Yeah.
later.
Great job.
Agree.
Thanks, guys.